it's not that stable.
Okay, thanks a lot, Doctor, for your presentation. Could you please permit us whether to upload your presentation in our YouTube channel?
Sorry, YouTube channel.
Yes.
Yeah, I think you can.
Okay. Okay, Doctor, your conference material will be collected by Professor Pian Xiao.
Yeah, Professor Chai.
Yes.
Yeah, thank you so much.
Okay, no problem, Doctor.
I remember now, just now, one of the participants want to ask a question, but since his internet is not that stable, I asked him to write in the chat box, but since now I didn't see any comment yet, so I'm not sure whether should I wait or should we just proceed with the other presenter.
So actually, the other presenter is waiting.
Okay, then we can just proceed. I will stop sharing my slide now.
Okay.
Wait, how to stop sharing? Oh, here.
Okay, Doctor.
Okay.
So let's move on to the next presentation. I would like to welcome Dr. Deepa Lakshmi Chandrasekaran from India.
Yes, thank you.
Okay, so Doctor, please go ahead with your presentation.
Hi, I'm Deepa Lakshmi Chandrasekaran from India. My presentation is actually on Maxwell equations and its applications based on new implication in material science. That is, normally new materials have been invented so far. That is mainly, as of today, metamaterials form the major groups. That is, they are characterized by negative permeability and negative permittivity. That is, negative refractive index materials they are called. So these materials, how we are going to apply Maxwell equations to this kind of materials and getting the result, and what are the applications we can will be the outcome. What are the applications that will be the outcome of these results when we apply the Maxwell equations to these materials. So normally, as we can see, what are Maxwell equations? As you can see in the screen, del dot D is equal to rho. That is the total electric flux coming out of any closed surface is equal to the net charge enclosed by that surface. That is the Gauss's law of electrostatics. Gauss's law of electrostatics, where it finds its application, this Maxwell equation finds its application mainly in capacitors. So each Maxwell equation is an application in electrical engineering. That is, as you can see, Faraday's law of induction is nothing but an application of transformer. That is a static machine which is normally used in electrical substations mostly. That is transmission. Both input and output will be separated, but there will be a magnetic link between this input and the output entities. Okay. So similarly, Ampere's law is nothing but both current, that is DC current and AC current, will produce magnetic field. That is the main application in Ampere's law. So each Maxwell equation is an application, and the result of the Maxwell equation is an outcome that can produce several applications when used fruitfully. Okay. So what we are going to see here is Maxwell equation. As you can see in these Maxwell equations, there are two parameters mainly. That is D, electric field intensity, and B, that is magnetic flux density. So these are the two parameters in these Maxwell equations. So these Maxwell equations contain epsilon naught and mu naught. So these are nothing but material parameters. They are not only for free space. For free space, epsilon naught and mu naught are characterized by some constant values. I'm not going to mention it, but if you all knows that is mu naught is 4 pi into 10 power minus 7 Henry per meter, and epsilon naught is nothing but 8.854 into 10 power minus 12. That is some unit. You get it? So these constants are nothing but material constants. So Maxwell equation depends on material medium. So according to the parameters in the Maxwell equation, the result of the Maxwell equation will change. So they incorporate permeability and permittivity. Okay. So what is permittivity and permeability? That is what we are going to see. So my presentation is mainly based on both of these parameters when they are negative. Okay. So permittivity. Let's see first. Permittivity. So what is permittivity? Permittivity is the ease in which the material can be polarized in response to an applied electric field. So it is more related to charge density. It is more related to charge density. Stationary charges create electric field. So this is the common explanation for permittivity. So it is more related to charge density. Density, that is the perfect term for permittivity. And permeability is nothing but is the ease in which the material can be magnetized in response to an applied magnetic field or a magnetic field. So it is closely related to kinetic energy. That is, moving charges create magnetic field. Stationary charges create electric field. Moving charges create magnetic field. That is, magnetic field can be created only by current. Whether it is DC current or AC current, it is the flow of charges which is only creating the magnetic field. Okay. So now, so this permittivity and permeability, as of today, metamaterials and optical materials, plasmonics, for example, metals have negative permittivity, that is plasmonics, and some ferrites, some of the ferrites have negative permeability at microwave excitation. So some materials, artificially engineered materials, have negative permeability. That is, normally in ferrites we have negative permeability at microwave excitation. That is what we are going to see in the coming slides. That is during ferromagnetic resonance. That is, when you give microwave excitation to the ferrite core, you are actually getting a negative permeability property. So that is what is going to be explained in the coming slides. Okay. So what is permittivity? Next. So Maxwell equation for negative permittivity materials. Okay. So Maxwell equation for negative permittivity materials. So what are negative permittivity materials naturally present here? It is ferroelectric materials. So ferroelectric materials come under the class of piezoelectric materials. So piezoelectric materials are further classified into ferroelectric materials, pyroelectric materials. So these classes of materials, that is ferroelectric materials, have negative permittivity. Okay. So how this material are characterized by negative permittivity? What makes them to have this negative permittivity property? That is, they are characterized by a spontaneous electric polarization. How they are brought up, how they are actually coming. That is, chemistry behind the spontaneous polarization. That is, in a crystal, the ions, for example, one of the ferroelectric materials is barium titanate. So barium titanate, in the crystal structure of your barium titanate, as you can see here, the barium titanate ion and barium titanate, barium ions, titanate ions, and oxygen, titanium ions and oxygen ions, they are displaced inside the crystal structure such that they are displaced with respect to one another, not symmetrically. Asymmetrically they are displaced. With respect to each other, they are not symmetrically displaced, they are asymmetrically displaced. Therefore, any one of the region has more charge when compared with the other region, which creates a dipole moment, whether it is displaced in one side, that is front or back, up or down. So that is depending on the x-axis, y-axis, that is space and time. That is, for the barium ion is displaced with respect to the titanium ion in a asymmetrical way, or oxygen ion is displaced with the barium ion in asymmetrical way. So these ions are displaced asymmetrically, which results in a net dipole moment That what gives it a spontaneous electric polarization. So it's a displacive phenomena. It's a displacive phenomena. Order, disorder, behavior in a material. Okay. So this polarization, this type of spontaneous polarization can be controlled by an externally applied electric field. So that's what makes it very useful. This property is what makes ferroelectric materials very useful, because using this control only, that is the polarization switching by an externally applied electric field, this is the application we are going to find out from this property. That is, this property will give you some application. For negative permittivity materials, polarization occurs in such a way that it aids the externally applied electric field. Normally, the electric field and potential are negative of each other. That is, you have from high potential to low potential, not from low potential to high potential. So electric field is actually directed from high potential to low potential. That is low potential minus V. That is V out minus V in, that is negative. So electric field and potential are negative of each other, but in this negative permittivity material, since the polarization is opposite, since the polarization can be switched from its sign, either positive or negative, we can get both of these cases. Either it aids the electric field or it opposes the electric field. So in this case, I am going to describe about how it aids the electric field. Okay. So let's see. So how that is ferroelectric. Ferroelectric, how it can be used as an insulator for a capacitor. So how it can be used as an insulator for a capacitor, that is sandwiched between the two parallel plates of a capacitor. Okay. So when this ferroelectric is sandwiched between the two plates of a capacitor and you are applying D, that is D is positive voltage. In this case, positive voltage. Positive voltage will cause a negative charge to get induced in the plate of a capacitor, and negative potential of the other side of the battery will induce a positive charge on the another plate of the capacitor. So this is the two plates of the capacitor. Positive voltage will induce a negative charge and negative voltage will induce a positive charge. That's why C and Q are of inverse signs. That is, if Q and V are inverse signs, if Q is positive, V is negative. If Q is negative, V is positive. So in this case, they are related. That is why we are going to get negative capacitance. Okay. So let's see the next slide. So capacitance equation, negative capacitance, that is C is equal to Q by V. Q is equal to minus CV. For a parallel plate capacitor, we have the equation C is equal to epsilon A by D. We know that. So where epsilon is the permittivity of the medium. Here what it comes? Ferroelectric material, which is negative. Okay. So, and A is the area of the parallel plate capacitor. D is the distance between the parallel plates. So this is the normal capacitance equation. Okay. So next move to the next slide. So enhancement of voltage, as you can see here, electric field, you have negative, you have positive charge, negative charge. And in between, you have polarization in the ferroelectric. That is, positive will induce negative, negative will induce positive. And finally, there is a circulation movement, that is positive to negative, negative to positive, circulation movement. That is, it aids the externally applied electric field. This field inside the ferroelectrics, this field inside the insulator, that is ferroelectric, which is used in a capacitor, will aid the applied, externally applied electric field such that there is a locally enhanced voltage inside the ferroelectric or insulator in a capacitor. That is ferroelectric, which is used as an insulator in a capacitor. So there is a locally enhancement of voltage inside the ferroelectric, which is used as a dielectric in a capacitor. Okay, so that is what it's explained here. And as you can see here, where I explained plus to minus, minus to plus, there is a circulation of electric field, circulation of electric field. So as you can see, so this is I have taken from one paper, spatially resolved steady state negative capacitance nature. So they actually did this. They actually spectroscopy, using spectroscopy methods, they did this experiment. And finally, they resolved the spatial components of the electric field inside the ferroelectric. So it's like this curl. That is, it's not diverging, it's a curl. So curl nature of electric field in ferroelectricity. So we already told that there is an enhancement of voltage. There is an enhancement of voltage. Therefore, Kirchhoff's voltage law is not valid in the circuit involving negative capacitance, and hence there is enhancement of voltage in the local regime. That is, the equation is given by, that is the curl equation. Normally, the curl of electric field exists only if there is a rate of change of magnetic field. But in this case, even in static conditions, we have the result of the curl of electric field as a enhanced voltage in the local regime in ferroelectric. That is V. Okay. So Kirchhoff's voltage law will not be applicable in the circuit involving negative capacitance. There will be a residue, there will be a voltage. There will be some finite voltage according to the capacitance value and the charge value. Okay. So behaves more like an inductor. Why negative capacitance behaves more like an inductor? Curl is the essence of magnetic field, and divergence is the nature of electric field. Hence, the negative capacitance exhibits inductive-like nature. Why? The closed loop is like closed circuit. That is closed loop, as I already seen here. Closed loop is like a closed circuit. Flow of charge in a closed loop, which generates current. Is a current. The closed loop of charges is a current which generates a magnetic field, and this may lead to a capacitive inductive transition, since current is actually produce magnetic field. Current actually produces magnetic field, and therefore it stores electromagnetic energy instead of electrostatic energy in some cases. Mostly both will present here. But electromagnetic energy mostly present because it's like a curl of electric field. Okay. So it is related more to magnetic field. So what are its applications? Immense applications. That is, it can be used to generate negative capacitance by using it as a dielectric in a parallel plate capacitor, which can be used for DC voltage enhancement in the local regime. Ferroelectric capacitors can be used to replace bulky inductors in an electronic circuit. Normally, power electronic circuits involve bulky inductors. If we replace this by a ferroelectric capacitors, the area will be reduced and power dissipation. So all those factors will come into a favorable scenario. And therefore, ferroelectric RAM is nothing but this has a spontaneous polarization, and it can be switched. That is in both ways, either positive or negative. Therefore, that can be used in non-volatile memory. Non-volatile memory that can be used in non-volatile memories. And Argonne Labs in USA designed a negative capacitor which can be used to achieve net zero transmission loss. So installing negative capacitors suitably along the transmission lines can help in reducing transmission loss by avoiding voltage drops along the lines, transmission lines. Therefore, we can go for net zero transmission loss. So these are the applications of ferroelectric materials. So the main change here is here, the Kirchhoff's voltage law will not be valid. That is in circuits. If it involves negative capacitance, there will be an outcome of voltage. And finally, so when we see what we are going to see is negative permeability materials. Normally, it occurs in ferrites at ferromagnetic resonance. So this is the why I have taken this ferrite is that this ferrite is actually used in transformers and most of the applications, and it is a very common material. So I am actually taking this problem, that is ferrite, and how we are going to achieve room temperature superconductivity in ferrite by exploiting the property of achieving negative permeability at ferromagnetic resonance. So that's a problem I am taken. So what's the proposed arrangement I am actually proposing? This is a proposed arrangement I am actually putting forward. That is actually, this is the ferrite core and microwave excitation to achieve ferromagnetic resonance for negative nu. That is, this coil around the ferrite core is actually given microwave excitation, and one end of the core is tied to a support, and another end is actually, I am actually applying DC voltage. So there is interaction between DC electric field and AC magnetic field, microwave magnetic field and DC electric field. So DC electric field and AC magnetic field, microwave magnetic field, it what creates magnetic ferromagnetic resonance. So that is Einstein-Degas experiment. I am taking it is for reference. That is Einstein-Degas experiment. Microwave excitation is given to the coil which is wound around the ferrite core in order to achieve ferromagnetic resonance. So microwave excitation, microwave is near to radio frequency and infrared range. Therefore, the infrared energy will participate during this transition. So this also is very important. This thing is very important because the infrared transition is what makes the material negative permeability. That is, I'm going to explain in the coming slide. So an FMR signal, why it is occurring? Why I am giving microwave excitation to the coil around the ferrite core, and I am applying DC electric field to the ferrite core. Okay. So I'm getting ferromagnetic resonance. Why? It is mainly due to Zeeman splitting. That is anomalous Zeeman splitting of energy levels. And the transitions, that is the magnetic electron transitions between these energy levels, it what mainly causes this ferromagnetic resonance. Okay. So it also depends on a number of magnetic properties, that is gyromagnetic ratio, saturation magnetization, magnetic anisotropy, and applied external magnetic field. So next, so anomalous Zeeman effect. For example, as you can see here, this is spin ice, that is dysprosium titanate, I think so. So the anomalous effect appears on transitions when the net spin of the electron is non-zero. Net spin of the electron is non-zero. Normally, the spin of the electron will result in a zero value, but in spin ice or in, as I am going to take this case as an analogy to achieving negative permeability in ferrite. So how this is analogous, that is I am going to explain. So there is a net spin movement. There is a net spin movement. So how it is achieved? The orientation of the magnetic moments, considering a single tetrahedron within the spin ice as in figure. So it's a tetrahedron. Magnetic moments obey the 2 in 2 out. That is, when you see a spin, you have from in to out, from in to out. So 2 in, 2 out. 2 in, 2 in, 2 out. So this is the spin moment. But if a thermal fluctuation caused one of the bottom 2 magnetic moments to flip from in to out, and one would have a 1 in 3 out configuration. So thermal fluctuation is brought in this case. That is, in this case, microwave excitation is given to the coil, infrared energy. So thermal fluctuation in this case is caused by this microwave excitation and ferromagnetic resonance, and therefore I am having a net moment. I'm having a net moment, and therefore it will result in negative permeability. So that is hence a positive divergence one could assign to a positively charged monopole of charge plus Q. Flipping the two bottom magnetic moments will give you a 0 in 4 out configuration, the maximum possible outflow. Okay, so this is the case. So this is the case why ferromagnetic resonance and due to microwave excitation is actually occurring due to Zeeman splitting, and Zeeman splitting involves some infrared energy which actually causes this negative permeability. Next slide. So the negative permeability occurs when the ferromagnetic resonance of the ferrite taking place. So it's a negative permeability. Therefore, what will happen is when you're applying an external magnetic field, or you are producing a magnetic field by applying an external electric field, and this electric field will affect this ferrite core because normally electric field, when there is electric field, there is magnetic field. That's what actually Ampere's law is about. When you are having a current flowing through a ferrite core, it produces magnetic field. When a current flowing through the coil, it produces magnetic field. So these two magnetic field, coil produces one magnetic field, that what leads to negative permeability, and you are applying a DC electric field to the ferrite core, that will also produce a magnetic field. So the DC magnetic field will get cancelled by this ferrite core, that is ferrite core, because it has negative permeability. It will act as shield for this DC magnetic field. It will act as shield for this DC magnetic field, and therefore there will be no and also as the case, it is having negative permeability, it won't have any magnetic field inside the core. So what will happen is that, so this is what I explained here. Unlike normal superconductors, the superconductivity in this case can be achieved at a normal ambient temperature. So there is no temperature arrangement or pressure arrangement to achieve this. That is, the temperature should be maintained at minus degree Kelvin. So that's not like that. It's a high temperature superconductivity. Okay. So at negative permeability state of ferrite core, on applying DC electric field, the magnetization due to it results in cancellation of the incurrent magnetization of the material, resulting in B equal to 0, and the core stops rotating. Normally, during magnetization in the Einstein-Degas arrangement, the core will actually rotate during magnetization. Change in magnetization will make it to rotate. But in this case, you are applying a DC electric field, and due to it, DC magnetic field will get produced, and this won't get rotate since total magnetization becomes 0. And therefore, what will happen is radius of curvature of the moving charge in a finite magnetic field. So moving charge in a finite magnetic field, R is equal to mv by qb. This is from Lorentz law of force. So R is equal to mv by qb. R is equal to infinity, which is a straight line. The ferrite core will remain stationary, and will there be no rotation. So normally in magnetic field, you have curl is equal to current, but in this case, there is no internal current. You know that, so in superconductivity, there will be no internal current. The internal current will be cancelled by the external current, and there will be no force on the charge carriers inside the material. So curl is 0. Curl is 0. Normally for magnetic field, curl exists, but there is no curl here. So there is a possibility of divergence since there is no curl. There is possibility of existence of magnetic monopoles. As I already mentioned in the spin ice, there is a net spin moment. And major breakthrough application will be room temperature or ambient temperature superconductors. So these are the equations as a result of negative